Welcome to my channel. In this video, I'm going to walk you through an example on magnetic dipole. The magnetic dipole is vertically oriented. The current, the magnetic current is I of M. The length is L. The length is L. The dipole is at the height of h, about the perpendicular ground plane. So our job is to find out the field components, the electric field and magnetic field. We also need to specify the region, because below the ground plane there shouldn't be any electric field, there shouldn't be any magnetic field. So in other words, if I'm going to draw the setting of this question, you have an antenna, dipole, you have a dipole. In order to produce a vertically dipole, you need a current loop. The current loop should be horizontal. So for example, in any particular time instant where you have a magnetic dipole pointing upward, this means the north pole is at the top. Then by the right hand screw rule, you should have the current flowing in this direction. And you have a ground plane. The ground plane so this is the ground plane. The height of the antenna is h. The current here is Im. Remember, magnetic current is not the same as electric current. Electric current is the current of electrons. It is the current of electrical charge. But magnetic current is the current of moving dipoles. Moving magnetic monopoles. So the length here is L. And in order to produce a zero tangential electric field, you need to have an image which produces a current in such a way that it counterbalance, it cancels off all the magnetic field, all the electric field on the ground interface. So for example, in this scenario, you might have a electric field in this direction. Then you should produce a electric field in a opposite direction. In order to do that, the only way that you can do is to have another dipole, which is an image dipole, pointing in the opposite direction. And if you do that, then the current that produces this dipole will be opposite. And obviously, the position of this image dipole should be h below the ground plane. So I hope this is clear enough for you. What we are going to do is to work out the far field. Because you have an actual physical antenna, you also have a image antenna. Both antennas will contribute to the far field. So suppose that this is the ground region. So the length here is R, and this one is R1. Yeah, the physical antenna. And if the observation point is here, then the pathway of the length of this pathway is R1. The length of the pathway between the image antenna and the observer is R2. So I can quickly say that there's the path difference. The path difference from here, based on the information here, it should be h cosine theta, if theta is the angle here. So this is the length. Similarly, the length here is also h cosine theta. So the actual antenna, the actual physical antenna, together with the image antenna, have the spacing. The total spacing is 2h. And because of this spacing, and because of the arrangement here, it produces it end up with a antenna array with 2 elements. So our job is to work out this. Okay. So we are going to write down the electric field contribution towards the observation point by the physical antenna and the image antenna. Okay. So this is the next job. So before doing anything, we need to find out the formula for the formula for the dipole. First of all, according to the formula for magnetic vector potential, the electric dipole has a magnetic vector potential given by, has the far field given by j k I naught, where I naught is the electric current and R is the length, and jkr and then sine theta. So this is the formula for the electric dipole. So the electric field is pointing in the azimuth direction. So this is the electric dipole, but we are now actually dealing with magnetic dipole. So we need to use the principle of duality to work out the electric field and magnetic field in the far shown. So the formula under the principle of duality, we know that E will be converted to H. H will in turn converted to minus E, and I electric will be converted to I magnetic. So the electric current will be converted to magnetic current under the principle of duality, and the characteristic impedance will be converted to characteristic admittance. So based on this information, we can immediately write down the magnetic dipole. So H and theta will be and this one, yeah, J, and the intrinsic impedance will become intrinsic admittance. So K and I naught will become IM, the magnetic field. Length will be unchanged, and 4 pi r, and then E. So this is the magnetic dipole. So this is the quickest way to find out the electromagnetic field. And for the electric field, it will be like this, and then it will be the electric field divided by this. So it will be this one multiplied by this. Okay. And in this case, what I get here is the electric field is multiplied. So the only change that you need is this one. So this is the electric field for the dipole, and this is the magnetic field for the magnetic dipole. Okay. So now the next thing that we can do is to find out the image. By the way, the electric field works based on the information here. This one should be converted to minus. Okay. Now, what we are going to do is to work out the antenna array factor. As we know, the magnetic dipole may be like this, and the ground, the image will be pointing in the opposite direction, and this is the setting, the setting of the question. And for the far field, we know AF, right? I should say AF is equals to the electric field due to the dipole at height h above the ground. And according to what we have done previously, we already found out is like this. So minus j k I m L 4 pi r and then 1, and then j k r 1. The other antenna will be in the opposite direction, so it's fair to say plus k I m 4 pi r2. So this is what I think. And when both add together, when we multiply it by psi beta, so this is the total contribution of electric field in the as detected by the observer. So we are going to simplify this equation. And first of all, R1 and R2 will be more or less equal in terms of magnitude approximation. And R1 will be minus and then kd cos theta. Sorry, I should say R1 is equal to R minus kd cosine theta, and R2 is equal to R1 plus kh cosine theta. So these two equations is for phase approximation in our derivation. So we are going to substitute R1 and R2 from this formula into the phase. We are going to use R1 approximately equal to R2 approximately equal to R to approximate the magnitude. So in other words, if you ask me to continue, I will just say AF will be equal to, we are going to extract all the light term, IM and L and 4 pi. Now R1 for magnitude approximation, R1 and R2 are approximately the same, approximately equal to R. So this is what we are going to get. And then here, and we are going to substitute R1, right? We will use these two formulas for phase approximation. So R minus kh cosine theta, and then plus jkIm L 4 pi. Again, right, R2 will be equal to R in terms of magnitude approximation. And then similarly, R plus kh cosine theta. And then the whole expression will be multiplied by sine theta. So this is the next step. So the final step is just to simplify this expression. I mean this one. So I'm going to do it, right? So from here we can say AF. Yeah, we can extract all the light term. And in terms of the phase, we also get light term here. K arrow, yeah, I got it wrong. So it is minus jkr, and then So this is what we can get. The formula will be getting simpler and similar. The next thing is to simplify this expression. It is very obvious. This one can be simplified into sine. And I forgot sine theta as well. We need to multiply this. So j, k, r, and then sine theta. And here it will be 2 sine k h cosine theta. So this is what I think. This is the final expression for the far field from the dipole antenna, from the magnetic dipole. Okay. Let's see what can be done next. Okay, the electric field. The electric field, yeah, the electric field, and this one is the magnetic field, will be equals to electric field divided by the impedance. So it's just like this. There are many things you can do at this stage. K is known, 2 pi divided by lambda, but H is not known. You can either use this expression to find out all the nodes if H is known, or otherwise you can use this, use the particular position of node and then find out the height, the required height of the magnetic dipole. Magnetic dipole means the current loop. Okay? So if you have no question, then I have one more thing to solve. The region, the angular region where the fields are valid. So this is something tricky. B. You have a current loop here, and this current loop will produce a magnetic dipole. And magnetic field can penetrate through the ground plane, but electric field no. So in terms of the electric field, you may think the electric field will be up to here. So E or V is a function of theta and phi, where theta will be between 0 degree and 90 degree. So this is very important. Yeah, we have to bear in mind the angle is only 90 degree. And how about phi? Phi is okay. Phi can be 0 to 360 degree. So this is the specification. And the image, right? The image is just an image. There will be conceptual magnetic current, but it doesn't mean this is the current is physically measurable. Okay? If you have any question, please leave your question to the comment section of this video.